Okay, let's share screen. Good. So good. So let's. We are talking, continuing or understanding about the trees. So last time we talked about trees, the tree structure, the way that we can represent them. And in particular, we talk about this binary search trees previously. Good. So, and we discussed that we can represent actually these trees in two ways. I mean, one essentially is generally you can have some kinds of vectors or array of lists. Then you are saying for each person, for each node, you say who is the parent and then who are the children. That's the typical things that you can do it. We will consider some, this is more explicit version. We talk about more implicit version when we talk heaps today. But before that, we talk about binary search tree. This is something that we discussed that C++ map has been essentially is using it. And it has these dictionary operations, which are search, insert, and delete. And we discussed this idea that all of them, the complexity of all of this depend on the actually the length, the depth of this tree or the height of this tree. So, so the depth and height we are essentially using for the same purpose. So, and if these are balanced binary trees, what's the meaning of balance? That I mean, it is somehow that's actually the definition that we want to have it here. What's the meaning of the exact definition of balance? If it is a complete binary tree means that every node has actually exactly two children, maybe except so everything is complete except maybe the last one. The last one, I mean, you may have some of this guy and then you don't have the rest. So that is called essentially complete binary tree. That we talk about heaps today, and they are actually like that. So if it is not the case, of course, this is some kind of balance, and we can show that this one is the depth or the height of this is like where n is the number of nodes. In this case, because every operation is order, all of this search, delete, and insert are in order height, then the operation would be log n. The total running time would be log n. However, as with this, and this also happened, if you are, we know that if the keys are inserted in this binary search tree in a random order, so if you have it, you are doing a random order, that's somehow random order you can think about in a practical way. In a, like in practice or in real world, that would be essentially no such kind of adversary that gives you in a very bad order. And just give it in a random order. Then in that case, actually you can prove like the one for quicksort that shows that order log n is the actual, the expected length. However, in the worst case, as we discussed, you can give actually something like a sorted order. And if you give the sorted order, then the depth of this, so it is 1, 2, 3, 4. Then in that case, actually the depth of this binary search tree can be n. And then essentially order height or the depth or height would be order n, and that would be just too much. Good. Having said that, let's go to talk about the next thing, which are ABL trees. So what are ABL trees? So AVL trees are binary search trees which are somehow balanced. And how do we define essentially? So these are exactly the binary search trees, such that for every node, the difference between the height of its left and right subtree is at most 1. So if you consider any node, the difference between left and right is at most 1. And we are defining the height of an empty tree just defined to be 0. Good. So any tree that you are, any node that you are considering, it has 2 subtrees. One here, because it's a binary. And the height, the difference between this one is 0, which means that they are same level, 1 or minus 1. Between the difference. So that's the one that is one important thing. Now, they can have actually, they are not necessarily complete binary tree. They can have a different shapes, but still, this is the theorem that we have. The height of AVL trees is ordered like that. So with this property that I have mentioned, that everything is between -1, 1, and 0, the difference between height. I mean, one way you can use induction essentially, or the other approaches to prove that the height of these graphs, AVL trees, which are special binary trees with this property, is at most ordered like it. Okay. Now, the idea of AVL trees is that whenever the we are doing exactly the same operation that we discussed, that we have search, it would be easy. There is no difference between regular binary search tree and AVL trees. Exactly, we are doing the same things that we have mentioned. We will compare it with the key of the root, and if it is larger, we go to the right, less than, we are going to the left. And we are continuing this. So search would be the same. The main thing is that for insertion and deletion, when we are insert or delete into a binary search tree, we have, done, for example, for delete, if you remember, if this was an item, to make it, we went to go to the left child and then we go all the way right, or we went to the right child and then we went all the way left to find the correct person such that we can replace it. So we have already done that. Here we want to do a little bit more. This is some operation which is called a rotation operation. So when we are inserting or deleting, or whenever when we insert or delete, and if this property of AVL tree for some nodes are violated, then in that case, we are doing some operation which is called the rotation. And rotation essentially means changing the pointers, or more precisely, changing who is parent of whom. We change it locally such that the new graph, the current one that is violated, we will do it in a way that actually the new tree has this property. That's the whole idea of AVL trees. And these are some of the details of that. You can see it in the Introduction to Algorithm, a Creative Approach by OD members, or Introduction to Algorithms, TLRS. Or you can actually search other places. I just want to give you the idea, but then the rest, these are some case analysis that you need to do it, and what are these rotations. And you can actually see the implementation on the web. I'm not sure whether like the maps in C++, are they AVL trees or balanced or not? That you can check it. I don't remember on top of my head, but yeah. So, but they are binary search tree. But this is the good things about AVL trees, because for AVL trees, when we are doing these rotations, especially when we are doing insert or delete, we make sure that these properties preserved, that the difference between the height of this is at most 1. And then because of that, we know that always the depth is log n of the number, and n is the number of elements which are currently in the tree. Good. Okay. So let's see just some examples here, and then we can. You can see the other cases in the book, but here let me just give you some examples. We don't go through all cases. Here, for example, this is the case. So this is the same. We have a tree here. This is a tree that we have it here. Good. So we have this tree. And then we are inserting these new elements. Good. So say that this guy was h minus 1, I mean, for some h. And this guy was h. So from here to here was h. No, you're inserting, I mean, essentially, and this insert that was simple. Insert always, essentially, it went to be always inserting at leaf level. So we will go there and we are inserting here. Now the issue is that the height of this tree becomes, it was h, and now it becomes h plus 1. So it was h minus 1 before, and then it becomes h plus 1 here. And so the difference here, it becomes more than. Now, for example, for a, if you consider it, the difference would be more than 1. It would be 2. So whenever it becomes 2, we need to rotate it. So how can we rotate it? This is like a simple things that we are just mentioning it. Here, and some of them are simpler, some of them, I mean, you may need to. So this operation that you remember, so when we wanted to delete some guy, what was the idea? So we needed to go, I mean, when we want to delete this guy, we came here and we go all the way here to find this person that we can replace it. Some operations like that, it might be needed also in some of them, and some of these rotations, that again, you can check it. But here, like for example, a simpler one. So what is a simpler one? So you are inserting this guy. So you need to rotate it. So you need to rotate everything to the right, essentially here. Because here, in some sense, sorry. So here, it seems that the right becomes a bit heavy, and then we rotate it to the left such that everything is again in order. So how do we do that? So this tree 1, 2, 3, 4, these subtrees, we don't do any changes with them. And this guy, this new guy that has been inserted, still would be here. It would be this child. The only thing we are here, we are replacing the top guys, A, B, C. How do we do that? So here we had these things. So we had it A, B, and C. Good. So in that case, when we rotate it, you see what will happen? So we knew that B is less than A, because these guys are all less than A, and these guys are all, so these are all greater than A. Good. So here B becomes the root, the new root. So, and of course, all of the, and note that when we do rotations, we want to make sure that still the property of binary search tree is correct, that this property, that all these guys on the left should be less than the root, and all this guy on the right should be greater than the root for any root here. So here, I mean, B is here, so B will be here. 1 will come here. I mean, still would be the children of this. 2, we knew that 2, it was greater than B, but it was less than A. So safely, we can also put this subtree 2 as a left child of A. So that's the thing that we will put it here. So just, and then after that, A, the other child of A was C, and we keep C the same, essentially. So this part essentially keeps this exactly the same thing. We are just shifting, essentially, B becomes the parent of A instead of A becomes the parent of, instead of A becomes A, be the parent of B. And with all of this operation, you can do it in a constant number of operations, because you are essentially changing some pointers, or you are assigning, essentially. I mean, you can change the pointer, or you can just essentially, this is, again, even in Python, this imputable versus imputable. So this concept of pointers that we have, either it is in Python or it's essentially C++, no difference. It is just a few number of reassignments, and everything is ordered one. For some of these rotations, I mean, that for deletion or everything, you may do open order log n. But anyhow, log n is fine. And we have done it before as well. So these are some of the rotations that this is when you are doing insertion, this you may do it. And if you do it deletions, then you may need to, again, for the deletion is that you may delete some guy. And so this is the issue that you may, this might be, currently these are like the, so this guy, maybe actually, so it might be the case that this guy is already, it has only one leaf. So this is H, and this is H minus 1. And then you delete this guy. When you delete this guy, then this becomes H minus 2. There is a difference here. So in that case, also, we need to do some rotations here. Either the rotation would be to the left or to the right, such that we make sure that none of them essentially is heavier than others by more than difference 1. Anyhow, that's the idea. You can see all these operations, and I don't intend to go through the details of them because all of them are this kind of case analysis and easy to read. Now, one interesting thing is that, as I mentioned, all operations in AVL tree are in the order of height, which is order log n. Empirical studies have shown that the average search time in a AVL tree is log 2 of n plus 0.25 comparison. So it is almost optimum essentially when you do that. It's log 2n, there is no constant here. So this is not 2 times log n or something, just log n plus 0.25. And it is even less than 1. So in some sense, we are doing the optimal comparisons essentially to have this AVL trees implemented. And the good thing here is that now we are sure that we have this kind of balancing. And this balancing is the case that the difference between the two heights of two subtrees should be at most 1. But that guarantees that the depths of this AVL trees would be always order log n. But how the depth or the height is order log n, in practice, actually, it is even no constant here. It's just log 2 of n plus 0.25. Good. So that's about AVL trees, which are essentially next generation of binary search trees that they guarantee that the depth is also order log. Now, having said that, let's continue this one. So note that, okay, talk about search, delete, and insert. But there are these other operations like delete max or delete min. These also can be done in AVL trees or, for example, in binary search trees very easily. So how can we find a max of the whole tree? Please unmute and answer. So to find the max of essentially a tree, that would be very easy. You will just take essentially you will just go all the way to right. That would be the max. And then you will go all the way to left. That would be min. And we will go until we will find a leaf or actually a node that does not have any max right elements. That would be the max or the min element. And of course, the running time of all of them are order log n, which is order height, which is log n. Now, using this delete max and delete min, actually, we can do this operation of sorting. So using this binary search tree, we can find another way of sorting. And these are all comparison-based sorting. So that's actually the way that you can, this sort also, I mean, you can do it in this, you can get the sort operations essentially like in C++ or others if you have such a data structure. So how can we sort? So it is very easy. First, so you have elements that you want to sort. So this is the whole array that you want to sort. So first, you are fetching everything into AVL trees here. So you have n elements and you are inserting it into an empty AVL trees. What would be the total operations would be n times log, because each of them would be at most n log. Now, when you have inserted, then you are just running the delete min. So each time you are just deleting the minimum elements here, and you will insert it into a new array. So you just delete min. So you are just doing delete min, and everything goes to a new array. And that's it. So you are done essentially with this one. So you just insert essentially everything into an array, and then you are just doing delete min. You are doing n delete min, and you are just filling this one. Again, each of them would be order. So this was n log n, and this is n log n because you are doing n times log n, which is to delete min. So that's, you can actually, this is another algorithm that you can get n log n sort out of it. Any questions?
Is delete min, does it run in constant time? Since we just
no. Order log n. This is again delete min, as I mentioned. Delete min is just, I mean, the same thing that we discussed before. So we are just going here and we just go all the way left. Correct?
Okay, yeah, right.
And that would be just the depth of the tree or height of the tree, and then height of the tree and depth. When we can say depth of a node, or we can say depth of a tree, means the height of the tree. So in that case, either way, essentially would be order. This would be log n. So each of them is log n. N times log n would be n log n. So it would be n log n plus n log n. The only thing is that here, this is a comparison base. We are only comparing this one, but this is not an in-place sort. Why? Because here we are actually somehow first we are having the array. We will insert it here, and then we will delete it, or like we will do it into a new array. I mean, this is, you can put it in the previous array, but that this is AVL tree is something that we are not doing in place. This is a new thing that we need to add it. But anyhow, this is a sort, and this is a good one. So now we will, next we will, let me just, now we are, given that we are talking about heaps or priority queues. So let me just go back here. Good. Great. Now we are talking about heap and heap sort. So heap essentially is another binary tree that we are talking about. Is a bit different from the one. And in C++, STL, you can have the priority queue. That's exactly the heaps that are there. And so it is already implemented. But here we want to see again what is inside that, because when you what is inside, then you can actually do more operations with that and see what is the structure of that. So the operations that we have heap or priority queue are a bit different from the one that we have for binary search tree. Binary search tree is actually a good one that you can do all the dictionary operations. As I mentioned, map or dictionary in C++ or Python is implemented through that. Heap is another one, or priority queue is another one that is implemented. And here, the operations that we have are different. These are not necessarily all dictionary operations. In particular, we have these simple operations. So these are the data structures that they support some operations, and depending to the applications that you have it, you may use some of these operations essentially. One is the insert X. Here you are inserting a key X into the data structure. So you are inserting a key X into your data structure. This is insert X. And the other one is remove. So we have this operation, you have key X that you are inserting. The other one is remove. When you say remove, essentially either it would be dependent on, it can be the max remove or min remove. And that's when you create a priority queue. For example, in C++, you can say the max priority queue or min priority queue. When you remove it, you will remove the largest key from the data structure. So in some sense, it is similar to, stack structures or something like this. So here we are inserting. There, you are inserting the top element, the one that, the last one that is inserted. Here, we are removing the largest key. Yeah, so you can, that's the thing, that priority queue, you can consider some kind of queues, which are, or a stack or something like this. And that's the, good properties of this priority queue or heap. And again, okay, so, and what is the heap property? So the data structure that we had it for binary search trees, we had this structure that everyone in the left is less than the root X, and everyone here is somehow, here is greater than that. What is the heap property? So the heap is this one, that everything. So here we know that the key of every node is greater than or equal to the key of its children. So here it means that X is, so everyone here is less than X and everyone here is less than X. So it is different from, so this is heap or priority queue, and this is binary search trees or ABL trees. And you see, there is a different structure between these things. This is a good one, actually. You can do it, search or other stuff there. But here, it is good for some properties, especially for the case that you want to insert, and at any time, you want to only delete the max guy. Okay. So let's continue this. Any questions so far? Is it clear? Please unmute and ask questions if you have. No questions? Okay. So let's talk about, this data structure a little bit more. Good. So let's go and a little bit again talk about explicit representation of trees. Good. So we talk about explicit representation of a tree, and what was the idea? The idea was that here in the explicit way, you have, when you have a binary tree or essentially generally a tree, then for each node you have essentially a vector or an array list. And here you have the node. These are all these guys, 1, 2, 3 to n. And then for each of them, you have a list. And this list, you can say the first element of the list is the parent, and the rest are your children. So this is an explicit way of essentially representing a tree. There are some slight variations that we talked, that maybe you just refer to the first child, and then the childs are just giving to the siblings if you want to make sure that size of this are bounded. But anyhow, but the one that we want to talk more about it is the implicit way. So that was the explicit way. Now, what about the implicit way? So the implicit way, essentially, this is, you can use it for binary trees, but you can actually represent it for any trees. So let's see what is this. So consider, for example, this particular tree here. So here, this is the implicit way that we talk about it. But you can actually represent the whole tree in just one array. So you don't need to have even tree structure. How come can we do that? We can do this one. Like you see, this tree, if you consider it, so you can give, this is the first element, this is the second element. So this would be the first array. So you can just number these nodes, 1, 2, 3, 4, 5, 6, 7, and then you don't have 10, you have 11 and 12 here. And so you just essentially have these numbers, and then each element here, like, because it is a unique number that each element has it, that would be that same array. So you can have an array like this. The first guy here will come here. Then the second guy here will come to here. Third guy is coming to here, and so on and so forth. So that would be one way to do it. More precisely, say we consider, I mean, let's have the exact formula. The issue that, I mean, if you do that, then you want to see, so you need to have this operation for each node generally. Who is the parent and who are the children? So we need to have some formula. We cannot do this one arbitrarily. Of course, for a given tree, we can do that. But if you want to have this kind of dynamic structure to delete and insert, then that's not, I mean, we need to make sure that we are consistent. So how can we do that? So if you have a binary tree, regular binary tree, so this one, this the first element, we will call it at the A1. So A1 children's would be at A2. A2 means array 2, array of set 2, or array 3. Then what about array 2 essentially? Who are the children of this guy? The children of this guy would be at A4 and A5. What about for this guy? For this guy would be A6 and A7. And so on and so forth. So if you have essentially AI here, then the left child would be at A of 2i. Right child would be A of 2i plus 1. What about the parent would be A of I div 2. Or essentially you can say this is the ceiling of I over 2. Sorry, the floor of A of good. So this is the way that we can actually implement anything, including this. Like we can just have an array, and you don't need to have any, I mean, pointers or any classes or anything. Just one array actually can represent a tree. This you can also generalize it for if it is like ternary tree. So this is binary trees that you have left and right. If you have a ternary tree, you can do the same thing. So if you have, for example, this is AI, then the children can be at A of 3i minus 1, A of 3i and A of 3i plus 1. And again, who will be the parent would be A of floor of I over 3. So you can do this one, and you can generalize this one easily for, I don't know, if everyone has 4 children, 5 children, etc. But you just want to have some maximum. Of course, you can consider the maximum n. But then the issue is that, so the issue is this one. This type of thing is good if we have the full binary tree. It means that all elements should be there. If not there, then the only problem with this one is that you are some of the space that you are not using in this array. And this can be the main problem. So let's see an example here. Good. So for example, if you see, say for example, it's a binary tree, if we have these elements, we have 1, 2, 3, 6, 7. So we don't have here, for example, this. These 4 and 5 are not there. So 4 and 5 are not there. I don't know. 6 also does not have any children, but 7 has 2 children. So you will see that this is the array of size 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes, but the array that we are using is here has size, needs to have size at least 30. The only thing is that the inefficiency of the use of a space, it means that there are some empty, so there are some places empty and we are not using it. So, and the issue is that in general, for example, you may have something like this, again, that you are only using these elements, just an a line. So an array of size n, if you are not careful, the space that you can have it can be 2 to the n. Because each of them, this is like from here to here, you are multiplying by 2, again multiplying by 2 in terms of indices. So the issue is that if you are not careful, then the index that you are using for just a binary tree of size n, it can be 2 to the n. So this is one way, but it can be inefficient if you want to do these things. However, the structure that we are doing here are the heaps. For heaps, I mean the one or the priority queues, we can use both explicit or implicit representation of the trees. The important explicit, of course, we can use it with no problem because there in the explicit we don't have this problem that the index essentially blow up to 2 to the n. But implicit, not always we can do it as I mentioned, but actually when we are for the heaps, because of the constraint that heap has it, we can actually implement it in an implicit way, such that whenever the size of the heap, so when size of heap is n, then use then you will use a space n as well. So this fact that for essentially n elements here, we are using the space, which is 2 to the n, that does not happen for heap. And of course, if it is the case, then we can do it. And there are some good properties that I mentioned. Okay. So what is this one? So for a heap of size, so we are assuming that we have an array of size 1, essentially size k, where k is an upper bound on the number of elements that a heap will ever contain. So we can say what is the maximum number of things that we are doing in a heap? 1,000, 1 million. And then we are using at most this amount of space. At any time, the space would be exactly the number of elements that we have. Okay, so, and we are talking about two operations that we are talking here. Let me just delete all of them. So, okay, so we have two operations here. One, we have it insert X. And we have remove. And the remove does not get anything, but generally it removes max or min. So here we are considering it is a max heap. Max heap essentially means that so max heap means the root is the largest. So for a max heap, it means that the root is the largest. Okay, so let's just see these two operations, remove and insert and remove. And as I mentioned, here we are talking more with the implicit version, but you can always do it in the explicit version as well. Good. But this would be more instructive actually to do it for using this implicit one, especially that we have seen the explicit one for binary search trees. Good. First, let's talk about heap, essentially remove, and then we talk about insert. So we want to, so this is the heap that we have it. And this is the largest guy, which is in the root, and we want to remove max. And we, as I mentioned, we know that all of this would be an array of 1 to k. Now, given this fact, and as I mentioned, AI would be, so the children, again, if you consider an AI, the children would be A of 2i and A of 2i plus 1. And the parent would be A of value of I over 2. Good. So, I mean, whenever I'm talking about children or parents, you can just use these indices to find the children or parents in the implicit things. Otherwise, if you have the explicit one, then you know who are the children and the things. So there is no difference here. So you can interpret both in the explicit representation or implicit representation. Now, you want to remove, so the largest guy here is A1. You want to remove A1. So how can we do that? So, of course, I mean, we can just remove A1. Then the issue is that when A1 essentially is removed, actually here, let me just use instead of K. Say A. So here, I'm just removing A1. The issue is that like the first element of the array, so this is an array, this is A, and this is A1, and then we have A. So here, A1 is removed. Okay, so we can remove it, but then what do we want to do? Because this element, this would be a hole here. So what we do, so that's the thing that we are doing it. So this is the A and essentially is here. What do? We bring this nth guy and we are just inserting it here instead. So we will just, so the remove X, so the remove essentially it returns A1 first, I mean, or keeps. So I say, I am assuming that the indices are starting from 1, but you can do it with 0 as well, no difference. Just put everything here, -1 would be from 0. But here, so in some sense, we are returning AI. But before returning AI, what do we do? Like A1. The A1 is the maximum guy. So we will keep the last guy, the N guy, and we will put it in the first place. So in some sense, how we are removing the maximum element that we will return it. But instead, the Nth guy we are putting here, and we are removing this last guy. Now, of course, the size becomes N minus 1. The only issue, so essentially it means that this guy is coming here. Now, the size became N minus 1. Everything is good in that sense. The only issue is that, what is the problem? The problem is that we want to make sure that the heap property is preserved. That's the main thing that we need to guarantee. So what was the heap property? So this is the root, and these are the two elements. And we knew that the root is larger than these two things. Now, we are putting essentially AN here. When you put AN here, this is the problem. If AN is larger than both of the children, then we are fine. We are done, essentially. And we have removed this one, because we removed A1 and we will put AN there. The problem arises when the case that AN is smaller than some of this. So it is smaller than this, or even it can be smaller than this guy. So in that case, what can we do? Then we don't have this heap property. AN is not the correct place. But what do? We will consider the max of the two children. So say this is the max children is here. Then we will say this max guy that is, of course, is larger than AN because AN was less than that, and also is greater than others. So I will just put the max child here. And then AN, I will put it here. In some sense, I am just swapping these two guys. And again, I'm just swapping because everything is in an array. I've swapped two elements of array. Or if you have an explicit representation, you are just swapping the values in the tree. Now what will happen? So this guy, now the max guy is coming here. AN is coming here. Okay, so we know that the max guy was larger than this guy because that was max by definition. And of course, AN was less than one of this guy. It means that in particular is less than max guy. So now for max guy, we are fine. So here, we are fine with max guy. So the root is fine now. Here, the left child, also we are fine. So we are fine because we didn't change anything here. So that we have the heap property essentially. The only issue is now is this subtree. That we need to make sure that the heap property is satisfied. Then what do? We just recurse on this subtree. So we just recurse on this subtree. Then again, you will consider this guy, this new guy versus the two children, and so on and so forth. So we may come again to here, to here, to here. But we know that the depth of this guy, because actually this is a complete binary tree, and these elements that we have it, always these are the elements that, all the elements that we have it, this is essentially a full binary tree, or actually it's called a complete binary tree because some of these last guys might be not there. So the shape that we have it for this binary tree is always like this. This is the one that I call it complete binary tree. So you may have this one, you may not have this one, but all other guys are there. That guarantees that the depth of this one is actually not even order, it is log n. So we know that the depth or height of this tree, that we implicitly have it in the array is at most log n. So it means that this comparison, these operations that we have done it, at most we need to do it the depth of the tree, which is order log n. So again, for the remove, what do? We consider the last, we are just essentially reporting the A1. Then we are putting A1 equal to AN. We remove AN. And then we are doing this operation, which is essentially pushing the this kind of top-down approach, that we will consider AI and then see if it is, everything is fine. If it is larger than both its children, then we are good, AN. If not, we are just replacing it with the max child and we recurse. And because the depth of this is log n, everything takes only log n times. Good. So is this clear, the remove operations? Please unmute and answer.
Yes.
Great. Okay, so let me clear everything. So that's the remove things. Now let's go to the insert case. So as I mentioned, so for the remove, we are doing so remove was a top-down operation. Good. So remove is a top-down operation. Why? What's the meaning of that? It means that we are from the top of the tree, we are come down. What about the insert is actually bottom up? So insert is, so this is essentially remove. And this is insert. So how can we do the insert? So insert, again, we are considering this one. This is the implicit representation. So we have this array A, A1. To insert it, we will go and then we will insert at the end of the array. So we are inserting, so we have an insert essentially X. This X, we will just increase n, the number of elements, and we will go it essentially here. So this is here we are doing it. So if we had it before, we had until n, now we have it n plus 1. And then we insert this new element X here. Good. So that's, again, insert, everything is fine. The only problem is that we want to make sure the heap proper. So what are the issues with the heap properties? So everything is fine for the heap. The only thing that has been changed essentially is this X guy. When X becomes here, as I mentioned, always you can find the parent of that if you go to A of n plus 1. So you will just go to the array of n plus 1 over 2. Value of n plus 1 over 2. So that's the parent. Or of course, in the explicit representation, we know some parents are here. So let's see what will happen here. So we have this this last guy, essentially X guy. And then we are saying is parent. Parent may have another child as well. Good. Now, consider the parent of this guy. See, we call it P. If X is less than, if P is greater than X, then we are fine. We don't need to do anything. Everything was fine. And the only relation between the parent and X that might be violated. Because that's the only thing that the parent should be greater than children. So if parent is greater than X, it is fine. If not, it means that P is less than, say P is less than X. So if P is less than X, then say this is another child C. We knew that C is less than P, so that we knew that. So we know C is less than P is less than X. So it means that we can just swap X and P and everything will be fine here locally. Because if we replace, so if X is coming here, and so let me just do it with a different color. X is coming here, and P is coming here. So X is greater than C, and now X is greater than P by definition. So this one would be fine. And nothing has been changed, except, again, the parent of this new X. So we will call it P prime. So we will see the P prime. Again, the same thing. If P prime is less than X, we just swap X and P prime and everything should be fine. So we just do this one. And this is exactly the thing that I have mentioned, bottom up. So you will come up until possibly you may even touch the root. If X guy, it turns out to be the largest element in the whole heap. How many operations do we need to do it? Okay, the operation would be exactly the depth of this or the height of it, which is like. So inserting each operation would be at most log n. You will just, again, start from the last guy. And if it is smaller, if it is larger than its parents, just you will swap it. And you will swap it all the way up. And you are done. Is this clear?
Yes.
So that's essentially the thing. So it's a very nice set of operations that we are talking about. This thing. And again, the logic behind it is very interesting because that's exactly the thing that you understand it, you will get familiar what are the way that the people have designed. If you need some other new structure, you may essentially just extend on top of this and do that. If you don't know this, I mean, then you cannot create that much on top of that as well. Good. Now, having said that, this is, let me just clear everything here. Now, let's go finally to the heap sort. Now, we talked about binary search tree, how you can use binary search tree to sort it. What was the idea? You will inserting all elements through a binary search tree, and then you just remove the max guy, and you remove the min, delete min, delete min, delete min, and you will get the sorting. So we want to do the same thing with the heap sort. So this heap sort, actually, one of the good properties of that, this heap sort is indeed is a sorting algorithm. It is as fast as quick sort in practice. And we know that quick sort, we knew that in expectation we had n log n, in practice was faster. But here, actually, heap sort is the one that worst case. So worst case comparisons here are ordered log n. Sorry, the number of n log n. So it is worst case n log n, and also it is in place sort. So we have seen actually like using the binary search tree or merge sort. All of them actually, both binary search tree is just sort them on, or merge sort, both of them were ordered n log n. But they were not in place sort. So here, that's the good things about this. Somehow this heap sort is the best type of sort that we have it, and somehow nicely combine the graph theory with sorting ideas. So it has n log n and it is in place. Let's see how can we do that. How can we implement it? So, so let me just clear. Actually, no, I don't need to clear that one. Good. So let's go and see what is the operations that we are. So here, you are given an array A. A1 to A. So the first thing is that, I mean, this is the array that is given and it is not sorted necessarily. So we need to, the same idea. The idea was the same thing that we had it before. So we wanted to somehow insert into a heap, into a binary search tree that we have done it. Now we want to do it in the heap, and then we want to delete it. But the interesting thing here is that we can do all of them in place. So the first thing is that we need to create a heap out of it. So how can we create it? That's actually very easy. So first we can say that the first element by itself is a heap. Then what do? Then we will insert A2 into the heap. So we are inserting but how can we insert actually A2 into a heap? Very easy. Exactly the same structure as before. To insert A2 into the heap, we just, I mean, what did we do when we inserted? We just add an element. We will put A2 at the as the last element, and then we will use this bottom-up approach to bring A2 up to the heap if needed. So we are doing exactly like this. So we consider this one, we are inserting A2. A2 actually is a correct place. You don't need to, it is already in the last element. So if it is needed, you will just bring it up into the tree. Then you are inserting A3. So A3 also you are inserting it and you are doing all the way the same thing. So essentially you are just inserting it A3, A4, until AN. So all of these insertions are happening actually as a regular heap operation. You just insert them one by one and everything is in place. So you are inserting A2. A2 is actually in the correct place. So you just bring it up if it is needed. A3 is in the correct place, is in the started with A3, and then you will bring it up to the heap if needed. The same A4, A5 to AN. What is how much is the total operation that it takes here is essentially this one. This is the log of I. Is it I equal to 1 to n. So why? Because when the size, I mean, when the size of the array is n, as we mentioned, the number of comparisons would be log n or log I. So we are, the size is first is 1, would be log 1. All of them are base 2. Then size would be 2, log 2, log 3 to log n. Some of this, and some of them we have done this calculation before, it is n log n essentially. So now we have the heap. So now that we have the heap, and of course, it's the array. Now, what do we do? Exactly the same thing that we have done it for binary search tree. we need to, from the heap, you want to create essentially a sorted array. But again, now you don't need, everything is this array, and this array A is already a heap. So what do we need to do? We knew that the max guy is A1. So instead of, so then we are just remove essentially, or remove max. So how do we do the remove max? So the remove max, so we knew that the max guy is here in the A1. We will just put this guy at AN. Or actually, in a better way, I just replace this one. So I will swap A1 and AN. So what will happen when you swap A1 and AN? So the max guy that was A1 now goes to the correct place of the array, which is AN. So you just, it goes there. So the max guy goes exactly to the place that it should go there. So A1, it goes all the way to here, which is AN. So A1 goes to AN, just swapping A1 and AN. No, that was exactly the definition of delete or remove max. So when we removed essentially A1, we just essentially A1 goes here. But instead of A1 going out, actually A1 goes to the last element. Goes to the correct place. So then you have an array of size n minus, a heap of size n minus 1, and an array of size n minus 1. You are doing again. The next max guy is coming here, the next max guy is coming here, and so on and so forth. So you just delete it, and this delete exactly actually puts the things in the correct things. Everything has been done in this array. So when we are doing, essentially these are the inserts. So we are doing the remove max here. So we have done how much, what would be the running time? Again, the running time would be the same number. So here would be essentially the running time would be sigma of, yeah, actually the running time would be exactly like this. Why? Because the size of the array first was n, so it was to remove was log n. Then it was log of n minus 1 because the size went down, log of n minus 2 to log of 1. It is exactly the same thing, would be n log n. What is the total running time? Would be 2 times that. So the total running time would be 2 times that, which is 2n log n. Or the number of comparisons. That's it. So we obtain an algorithm that in the worst case, it is 2n log n time, number of comparisons. So it's very fast. And it is the worst case. It's not the average case or like the expected case that we talked with the quicksort. And one important property of quicksort was that is an in-place sort. Here, this one is an in-place sort as well. You don't need to have a new data structure and essentially insert these guys in there. Again, this concept of in-place is used a lot, for example, in Python. If you are using pandas or sort or others, you need to say explicitly whether you want to get in place, like it means that the current one should change or you want to return a new things. So this concept of in-place is there essentially, and it is cute. How can we do this sorting essentially in place using this heap array? And these priority queues are used in lots of other places. That's exactly the reason that this STL, so C++ STL, actually have, as I mentioned, priority queue. Why? It is like a dictionary queue. So the idea essentially is this one, that this priority queue things is that yes, you have some good what this data structure, some of them were so useful that used a lot that they have implemented that became part of the standard C++ essentially libraries that you are using it. That was exactly the reason, because these priority queues, these maps, essentially, which are binary search trees, or like hashing, which are unordered maps, or other things, vectors and others. All of them are, the important one, are implemented in C++. And there are some modules for Python as well that you can use it. Dictionaries there essentially, or some of them are there, some you can use it, just some modules you can import it and use it. And these are the important ones because they are very useful, and at the same time they are like have a very good properties that we discussed so far. So this actually finishes this idea of sorting algorithm, sort and search. At the same time, we have, use graph theory so far. We have defined lots of graph properties, and especially for trees. So next, in the next sessions after the midterms, we are talking about, more graph algorithms in particular, and different type of algorithms. That also we spent some time on that one. And time permitting, we are also talking about MP hardness, etc. Good. So let me just stop shares. Okay, thanks everyone, and we are finishing the class.